Welcome to lecture 19. Today we'll be continuing with looking at Green's functions for the wave equation, and we derived the general formula for any dimension in the previous lecture, and today we'll look at specifically how we get the one-dimensional D'Alembert solution from the Green's function, and then in the second part we're going to be looking at the Green's function in 2 dimensions and exploring which properties are similar to the one-dimensional thing and which are actually dimensionally dependent. And it turns out there's similarities, but as I mentioned in the last lecture, they're fundamentally different kinds of solutions because of the dimensionality. In one dimension, you have this idea of a wave on a string propagating, and the wave remains the same once it's going, and then you have superposition. In 2 dimensions, you have the idea that you start with initial, say, bump, and the wave's amplitude decreases in some sense as the energy has a bigger and bigger region to flow into. But we'll make that concrete during the second part of the lecture. Okay, so just to remind you, we're looking at the wave equation. Typically, we have the functions and its derivative specified on a initial slice. If it's a one-dimensional thing, this is just a line, like over there. If it's a 2-dimensional thing, it's actually a plane that's indicated. If it's a wave equation in 3 dimensions, it is the function value over all 3-dimensional space. And then the time propagates upwards, as we depicted here. So at a later time, which is, say, for example, this light blue region, you want to know what the wave equation is. You once again have the spatial domain, which we denote omega t prime, and this domain's boundaries we are going to denote gamma prime. And we then also have the idea of the field point, which is where we want to know the function, as well as the source point q, and then the whole strategy is to try and write the solution at the field point in terms of an integral over the source point over a certain region, and we proved how to do that last time. And in fact, we proved how to write down the solution itself. So just let's make this as a little reminder. Here we have our wave operator is equals to a source, and the wave operator is in the prime coordinates over here, where our wave operator is what they call the D'Alembration, which is the spatial Laplace operator minus dtt over c squared. If you are doing relativity, you would just view this thing as the basically the 4-dimensional box operator. You would use it as one thing, and that's the reason why the operator got established. But for all practical purposes, if you haven't done relativity, just view it as the sum of these two. Okay, and we call that the wave operator in Rn, so it's true for any dimensionality because this thing is an operator that works in any dimension. And we then went about and found the symmetrical solution. So we started to look at solutions that are only dependent on the distance from the source. So we defined R to be R prime minus R and T to be T prime minus R, where R is a vector in n-dimensional space, where these i's are then the unit vector. And we showed that if we could solve the Green's function equation, which was basically an operator on the prime derivatives equals to the delta function of R, which is basically that R prime minus R, and the delta function of T, which is basically T prime minus T. And in addition, the operator was assumed to be 0 if T prime is greater than T. In other words, the operator is 0 above this. So this field point is only influenced by sources at an earlier time. So in some sense, it was a causality assumption of how we structure the solution. Then we had, for an infinite domain, we proved last time that we could actually write down the solution this way. And it was just a repeated application of the divergence theorem or Green's theorem to do that. Okay, so I'm now going to use this as a starting point, and we'll use it for the next 2 lectures, in fact. And the main thing was then to try and find the Green's function. And we did that too, and we showed that the symmetrical solution for the Green's function, which is the valid Green's function if we are working on an infinite domain, was simply to assume that the Green's function was not a function of 4 independent coordinates, but it only mattered on the difference between the source and the field point. Okay, and when we did that, we used the Fourier transform method, and we wrote down that in general, in any dimension, you could write down the symmetrical Green's function as 1 over 2 pi to the n, the integral over the n-dimensional space of 1 over k sine of t ck e to the minus I r dot k. Okay? And the thing now that remains is to evaluate this in various dimensions. And also last lecture I said in one dimension r is just the difference between 2 points on 2 coordinates on a line, and we showed that you could write down the Green's function in this way. Okay, so that we derived carefully in the last lecture, making use of the definition of our step functions in the Fourier domain. And that is one of the problems that you have for this week, is to actually look at that very carefully, and hopefully the problem makes it possible for you to sort of step it through by yourself. The main thing you have to do is just use the definitions we have in the previous slides for the delta function, the Green's function, to actually prove what the Fourier transform of the derivative of the step function is, and therefore what the Fourier transform of the step function itself is. Okay, so this is the Green's function in one dimension, formally derived from this expression. And what I want to do now is just to underline that it is in fact D'Alembert's solution if you go and substitute it in here. Okay, because it's not obvious just from looking at it that it's going to give you that, but it is in fact it. And it's a good way of, when we start looking at the two-dimensional case, seeing how we deal with the delta functions and the step functions that arise. Okay, so Heaviside step function. And so what this equation, if you actually do it, so when I get this expression like this, the first thing I do is actually see where the function is 0 and see where the function is non-zero. And this thing, I mean, remember, if you remember what the Heaviside step function is, if x is positive, it is 1. If x is negative, it is 0. And so wherever this quantity is positive, it's 1. Wherever this quantity, and 0 otherwise, whenever this quantity is positive, it's also 1. Okay, so if both quantities are positive, then this function evaluates to 0. If both quantities in this thing are negative, if both quantities are positive, it evaluates to 0. If one is positive and the other one is 0, it evaluates to 1. And if both quantities, okay, so that's what it is. And what happens is, if you have r, which is just the difference between the two coordinates, so the absolute value of x prime minus x is less than t minus t prime, then you have that it is 1. Okay, so this statement is equivalent to this one. Okay, and so you have that only for x minus x prime less than ct do you have ct, which is suppose t prime is 0, is less than ct, then this is equals to minus c over 2. So for example, in this picture, the Green's function will be non-zero at x on the axis, at x lying between ct and x prime lying between x prime minus x lying between ct plus ct and minus ct. Okay, so so what we have now is just once more an equivalent expression of this Green's function in terms of the absolute value sign. I'm just giving you the equivalent expression so you can also play with it. And what I then do is, in this, because I want to evaluate this function, I'm going to need the derivative of the Green's function. And the derivative of the Green's function is simply the delta function at the argument times the derivative of the argument, so you have a minus c coming in here. Okay, so this is the derivative of the Green's function. And what we have when we evaluate this integral is that this Green's function effectively makes that the only non-zero component of the integral is stuck in this region over here. So x minus ct and x plus ct if you want to know what the value of u is at xt. Okay, so you only have to do the integral over this triangle. And only in this region is your Green's function equals to minus c over 2, and for the rest, it vanishes. Okay, so that's what this Green's function says. The other useful thing is the derivative of the Green's function is actually only non-zero on these lines, right? Because that's what the delta function defines it to be. And so when we go about evaluating what this function is, u of x and t, we now have that the Green's function is minus c over 2, okay? So the minus sign is coming in there. You have the c squared over here that has been cancelled out with a c above, and you're left with 2c over there. And you've actually taken this Green's function definition of the step function and you've used it to restrict the domain from infinity to this integral, okay, times your source function x prime t prime, okay. So your source function is basically just being integrated over this whole triangle, and the way to write that down in terms of x and t coordinates is as follows, okay. So, and the next term is the contribution from the initial conditions. So at omega 0, which in this example is basically when t prime is 0, so it's this line, you have one contribution that comes from u times the derivative of g, and the derivative of g is just this delta function. Okay, so it is meant simply u evaluated at the 2 points in which this argument is exactly 0. And that argument is exactly 0 when x prime is equals to x minus ct and when x prime is equals to x plus ct. Okay, and so you basically have the function being evaluated at those 2 points due to the definition of your delta function. And then the final term is the contribution of the derivative of your initial condition, and that is merely minus g, so that is minus minus, so it's plus c over 2 divided by c squared, so it's 1 over 2c, and then it's the integral along this whole line, so it's x minus ct to x plus ct times the derivative of u with respect to t at x prime and 0. Okay. And this thing is exactly D'Alembert's solution that we derived earlier when we actually showed the function could be separated into two different functions, and we actually found the expression for those functions in terms of the initial condition. Okay. So, and as discussed previously, you have this idea in one dimension that you have this domain of dependence, basically all the points where anything happens that influences what the solution of x and t is, and you can see now that that domain of dependence is entirely determined by your Green's function structure. And that statement remains true in other, as we go up in dimension as well. Okay, so that's it for 1D, I think. Okay, and just the reference when we did the D'Alembert solution, discuss more of it, it's in lecture 6 and 7. Okay, now comes for the new stuff. The Green's function in 2 dimensions. Very similar process. The main trick is to actually be able to evaluate this integral in now 2 dimensions. and then to understand the solution, and then to understand how it differs from the one-dimensional case and what properties it keeps. And it's kind of interesting to see. And so when you think of a Green's function in 2 dimensions, think of an infinitely long, flat latex sheet, and think of an initial condition, which is like the initial shape of the sheet, and an initial velocity, which is somebody's banged it in a certain way. And then a source term can be like somebody with a stick under the sheet that runs around it, or a dog running under the sheet that actually forces the sheet in a specific way. And what we're going to work out is how the waves propagate on the sheet. And in fact, if you can imagine, say you start with a sheet that's flat and you have a stick that effectively is a delta function, you have a guy running around with a stick in a circle, you're going to have waves go out on the sheet. And this is exactly what we're going to be describing over here. And the Green's function actually makes it possible to do it in tremendous amount of detail. There's a power in understanding how Green's functions work, even though they are hard. I mean, I find them hard initially to evaluate and to see how they do it. There are other methods, and the next method that I'll teach you, separation of variables, they actually find much easier than this. But this one is very powerful if you actually want to work with solutions without knowing what the force in turn is explicitly, or without knowing what the initial conditions is implicitly. You can actually work with a solution without knowing the specific one, which is what makes them so powerful. Okay, so we want to evaluate that guy. And to do that, we're going to, the main tricky part is this thing, because now it's a vector quantity in R dotted with a vector quantity, and then this integral is over more than one dimension. And so what we're going to do is I'm simply very carefully going to go through all the steps that you can see how the dimension enters. So we're going to go to polar coordinates, and we're going to have our area element, then basically your dx squared dy squared in polar coordinates is just r dr d phi. In this case, the r is just a k. Okay, k goes from 0 to infinity, phi goes from 0 to 2 pi, and what we're going to do is we're going to choose the axis, and this I can do just to make the problem easier. So we're going to choose the axis to correspond with, so that the dot product of r dot k is equals to rk cos phi. Okay, if you didn't do that, you would have a phi 0, which is the 0 part of the axis, but I've just left that out. So we now know what this quantity is that enters up at the top here, and you can see already that it's going to be more complicated because you now have a cos phi in the exponent. Okay, so let's go on. Where r is the difference between the two, but that's not going to matter. So now in 2 dimensions, here is the integral. N is equal to 2. We're in polar coordinates, so phi goes from 0 to 2 pi, k goes from 0 to infinity. You have sine t ck times e to the I r k cos phi. Okay, so that's the integral, what we're going to evaluate. And you can evaluate it by any means. It's just eventually you get used to the tricks you use to make it easier. I've actually spent a lot of time getting stuck on trying to evaluate these integrals. So the way that I chose to evaluate it is I write out the sine tck as just the definition of sine in terms of the exponents, and the 2i goes out in the front there. Okay, and what I did now is, mainly because I know what I'm working towards, is I replaced this integral from 0 to infinity with an integral from minus infinity to infinity with a step function over here. Okay, so remember in the one-dimensional case, I took the infinite integral down to a finite domain by making use of the step functions and putting their boundaries. Here I've just done the reverse. I've put the step function, so this thing is effectively 0 from minus infinity to 0, and then 1 from 0 to infinity, so it's the same integral. And then I've combined in the exponent the two factors. And so the reason I did that is basically a property that you're going to work out in the problem set is basically if, you're not going to get that property. So first, I just want to give you a few more properties of the delta function. The first one is if you have, because you're going to need that in the problem set, if you have a delta function that's alpha times x, then you can prove that that is the delta function of x over alpha. And you can actually prove that using the limits that we had in our definition when we defined that delta function is the limiting thing of a series of Gaussians. So you can use that. And then another thing is, the reason I wanted this way is that suppose you now have g of x and it has a number of simple roots. In other words, you have a g of x, which is a function that cuts the axis at various points. The delta function of that function is just a function evaluated at those various points with a scale factor. Okay, so if g of x equals to 0, and therefore the delta function of g of x is the sum of the delta function of x minus xi, which is the zeros, over the derivative of g evaluated at those functions. I don't know if you've seen this before. No. Okay. It makes sense, but it's just rigorously defined this way. I mean, it's basically the delta function picks out all the points at which the function value vanishes, and then it just becomes the sum over there. Okay, they use this a lot actually in image processing and a number of branches of mathematics. But anyway, here is the rigorous definition, and I think you'll actually play with it a bit in the problem set as well. Now, the Fourier transform of the derivative of h of x, we proved right in the beginning when we looked at the derivative of a function general, it's simply ik h hat of k, and that was equals to 1 over 2 pi. So that's true. The thing is now, if you want what the Fourier transform of h of k is, then just at least the main is, it's basically 1 over 2 pi over ik, and that will be true everywhere except where k is equals to 0. And where k is equals to 0, you have to be careful, and you have to go back to your definition of your Heaviside step function and the definition of the Fourier transform itself. And that is something, how you prove this next result is also one of the problems. And there's actually careful steps that you go through in proving it, but the result that you should get is basically the Fourier transform of the Heaviside step function is just the thing that you get from this derivative expression plus the delta function at k over 2. Okay, so those are the additional properties. And the reason I gave that to you was that this thing basically looks like the definition of a Fourier transform of your Heaviside step function if you treat that combination as x. Okay, and that allows us to simplify this expression. So I'm basically going to replace this thing by its Fourier, by the definition of its Fourier transform, and or rather inverse Fourier transform effectively. And what I'm going to get is that it's equals to the delta function, the factor of 2 I've taken out. It's going to be equals to the delta function of this argument. Just be careful, I've replaced k here with my normal definition of the Fourier transform. I would have replaced, this would have been the x. Okay. So this thing, and so when I talk of k here, it is actually that thing. Okay. So this is the delta function, the Fourier transform of the first one. So, and I've lost the 2 pi over here because of the definition of the Fourier transform. So I've the delta function over here times a pi I, and the 2 I've taken out, times minus 1 over this thing, okay, minus this guy. Okay, so that's the delta function of the argument plus minus 1 over the argument over there. Okay, so I've basically just used the definition of my Fourier transform of the Heaviside step function. The next step that I do is these guys look kind of similar, and I'm integrating them from 0 to 2 pi, but there's this minus sign. So I'm now going to do a trick that basically makes them exactly the same. And what I can do is, because I'm integrating over the whole circle, for these last two, if you let phi go to phi plus pi, okay, then you're going to switch the sign in front of this thing and the sign in front of that thing, and so they're going to look very, very similar. And you're going to still be integrating over the circle, just shifted. So it's actually the same. So here I just want to write it down. So if you change variables, phi equals to phi prime plus pi in the last two terms, the domain of integration remains the whole circle. So just the same argument as you had in one of your problem sets. So you can keep it that way, but the sign in front of phi prime changes. Okay, so I'm going to do that, and the moment those two are the same, the d phi doesn't change, the delta functions cancel, and you're left with this, basically two of these guys. And so what I have is that the Green's function is just, the two-dimensional Green's function is just given by this integral of c over 4 times 2 pi squared, where the pi I've taken out, the imaginary parts have cancelled, from 0 to 2 pi 1 over r cos phi plus tc, and there's my Green's function. And what I'm going to do is I'm going to write this as c over something times r. So I'm actually going to take out r over here because the wave falls off like 1 over r. And times this integral I, where this integral looks like that, which is basically 1 over cos of phi, which is always 1, plus this tc over r. Okay, and so this is now the Green's function, and what actually remains is to evaluate what this integral is. Questions before I go on? It's intense, but it is useful to go through all these steps because they're tricks that you use when you look at high dimensional stuff, and you'll use it for the rest of your life. And especially if you do image processing or, in fact, electromagnetism and physics, you use it a tremendous amount. Okay, so I'm just going to introduce a new variable where you have this tc over r is minus a, and then this integral is just a classical second-year integral, or first-year even integral, hopefully. And its properties are that if a, the absolute value of a, is greater than 0, then it's non-singular. In other words, you have no denominators that vanish, and it's just an integral over a finite region, so you're always going to find an answer, which is a relief. And so we're going to look at that case, and then we're going to integrate that. You can actually just do it directly. You say z is equals to the e to the I phi, and you say dz is equals to I e to the I phi d phi, and then you have an integral that looks like this, basically in a complex plane now, which you can write this way, and you multiply the 1 over z through, and you basically have that integral. Okay, and this thing is just a rational function, and effectively you apply, just either solve it directly, or what you're effectively doing when you do that is you're applying the residue theorem. Okay, so when you have your rational integral, you write it as, you try and take out all the simple poles. So you're basically going to write it like this, z minus the one root times z minus the other root, where the roots are simply defined by solving this equation, writing down the quadratic formula for that equation. And the next step is to observe that you're integrating over sort of the circle. The z minus lies inside the circle, and z plus always lies outside the circle. Okay, because we've assumed a is greater than 1. So then using the residue theorem, you can basically write the integral like that, where I've broken it up into its, what do you call it? Partial fractions. Yeah. I've expressed basically this thing in terms of its partial fractions, and I only have to consider this one because it has a 0 inside the disk. This thing never goes to 0 inside the disk, therefore it's analytic, and it's 0, right? The integral around a curve of an analytic function is 0, so we only consider this guy. And to evaluate the residue, you basically have to evaluate the function that multiplies the pole at the pole itself, and because it's not dependent on anything, it's easy. And so we have the residue theorem gives us that it is 2 pi I times 2I, add z minus minus z plus, which the minus sign cancel up at the top there, and you're left with 2 the square root of a squared minus 1. Okay. You're sort of getting into practice how the complex plane becomes very important later in your life. Yeah, it's basically built into the fundamental structure of a lot of mathematics. And there are more, like Cauchy, when he worked that out, he really started understanding deeply what structures there are. People went further, and there are more complicated things than complex numbers, like the quaternions that form more fundamental structure. In fact, the boosts in general relativity, a lot of their structures actually comes directly from quaternions. So the complex numbers appear very naturally for Laplace's equation, especially in 2 dimensions. In 4 dimensions, the quaternions start becoming important. They have a lot of the properties in a subset of the complex numbers. So the techniques, like those ideas of what a holomorphic function things and all those things are really fundamental to the structure of reality. It's kind of amazing. And the techniques he used to actually describe it basically were the stepping board to develop Green's functions and to go on. So yeah, don't underestimate the value of them. So, okay, so there we have the integral. Nice and simple. We now have an analytic function for our Green's function, which is exceedingly wonderful because seems extremely simple. All the complexity is hidden in the A, right? So we have where A is just T prime minus T times C over R prime minus R, and remember that's the vector norm, okay? And so you have this Green's function entering in. Right. And if I write it out just to remind you that there is that complexity, I can rescale it a bit and I can express it in this way. Okay, so I've just multiplied through by R in the step function, but that doesn't make a difference because it's either, if it's positive, it's 1, if it's 0, otherwise. Over here, I've still got my a squared minus 1. And so here, I've just written its other disguise, because sometimes when I work with these things still, I start forgetting that this is R prime minus R, and it actually is quite tricky. I'm not going to say it's easy. It is quite tricky to evaluate these things, even though the Green's function is reasonably simple. Okay, but anyway, so here it is, just written out in another way where I've taken the R in and multiplied it out there. And it's your prerogative to choose the thing that's simplest for your particular example of evaluating. Okay, so now, just remembering what we had from writing the general expression for U down, we needed the derivative of G, okay, with respect to T prime. And here it is. It's simply the derivative of the step function, okay, with a minus sign coming in. So we have the delta function over the square root component minus the derivative with respect to t prime of the square root. Okay, and you can already see that it's going to start differing from the one-dimensional case. Whereas the one-dimensional case, you only had that. Here we still have this other component over here. We're going to need the derivative of r, but it's not obvious why. But just for completeness sake at the moment, I'm going to write down the derivative of the Green's function with respect to r, which is the difference between our source and field coordinates. And once again, you have your delta function coming in with a c dividing over here and the minus sign going out. And then you have the derivative of the square root with respect to r. And so the reason I wrote that down is I actually want to express, and it's going to become useful later, to express this Green's function's derivative with respect to t prime as a delta function plus a spatial derivative. So that's just an identity I wanted to give that comes from straightforward differentiation. But if you're in the thicker of the part of the rest of the problem, it's harder to see. Okay, so now what we're going to do is start evaluating what the wave equation does and what this Green's function actually means. And so the first thing to observe with the Green's function is that just like the Heaviside step function in the one-dimensional case, remember we had exactly this term in the one-dimensional case, there it confined the domain of dependence on that triangle, okay? This term, it's exactly the same Green's function, except the thing that's entering is not just the coordinate, it's the norm of the radius around your field point. Okay, so you want to know what the Green's function is, say at p of x and y, of p of r for a specific time, and so then that the Heaviside step function over there is basically restricting to the domain of influence to that cone that sits over there, okay? And the center of the cone is always r, and your this big R is the coordinate system that's based from R outward. Okay, and then phi is the angle of the coordinate system. Okay, so what we're now going to do is we're going to evaluate each and every term that entered here and to try and compare them to what happened to the one-dimensional case and to see what has changed. So what we're going to do is we're going to integrate over the whole plane, like the omegas are once again the whole plane, but once again the Green's function with the step function inside then restricts it to that cone. And so we're going to center our coordinate system at R, which is basically this field point. And we're going to have the direction of R define what the theta equals to 0 angle is. You once again don't have to do it, but it just made my notation shorter because I didn't continuously have to add an extra phi term. Okay, so the direction of R gives you theta is equals to 0, and then you have just R dot theta is equals to R cos theta. And so this is the normal definition. And so what we now have to do is we now have to start evaluating what the Green's function is. So here we write the same Green's function in terms of the R and theta coordinates. And so what this first term becomes is the Green's function evaluated at R, comma t prime, okay, and G, okay, and here's where it gets tricky. Remember when this definition is the integral over R prime. So here it is G evaluated at R prime. And so the argument that must go into G is r prime. Okay, but here r prime is simply little r plus big R over there. Okay, so the argument basically that's entering the Green's function and that's entering G are different. Okay, times the area element, which is just r d theta dr dt prime. And the same holds true for the other terms. So here we have u evaluated at r prime, which is r plus big R. So this is now the initial condition, right? Times the derivative of g evaluated at r at minus t minus the derivative minus g2 evaluated at r at minus t ut, but once again evaluated at r plus big R times r d theta dr. Okay, so simple, straightforward steps, but crucial to know that the two arguments are different, and crucial to understand that we've now chosen our coordinate origin at the actual source point. At the field point we want to know the answer at. And then the source point influencing it is just in this cone around it. Okay, and so the last step is to basically start massaging the actual expression of the Green's function a little bit so we can actually see what it means. And so the way I'm going to do that is I'm basically going to break up those three terms in the integral into three different parts and discuss each one in turn. Okay, so the first one is just the source point, the one with the forcing term, so the guy with the stick is over there. The second one is the one, this is now the initial condition where you have specified the initial profile, and this dg dt is going to be a bit difficult to evaluate. I'll show you how to do that. And then the third one is just where you specify the initial profile of the initial time derivative of the sheet, and this Green's function is reasonably easy to evaluate. Okay, so once again, this factor h that enters the Green's function constrains the g2 to the cone. So it's obvious how u3 and u1 basically gets constrained to the cone. This guy we have to be more careful with. Okay. Okay, so basically the upper limit for basically the constraining it to the cone is that you now change this integral to, in this particular case where t is equal to 0, it just becomes, or t prime is equal to 0, it becomes ct, and over here it becomes ct minus t prime over there. Okay, the evaluation of the u2 integral is a little bit tricky. And once again, the trickiness comes in that this thing is a vector. So there are two variables hidden in there. So the way I'm going to deal with it is I'm going to say, let s hat be the unit vector of r over r. So it's basically the unit vector that points from the coordinate origin, which is set at your source at your field point, to various source points. Okay, so I'm going to have s hat point in that r direction. And so a way to express your r hat, right, in other words, where you want to evaluate this integral, is simply to say it is r, which is the origin of the coordinate system, plus r, which is now a scalar, the scalar norm of the big R vector, times s hat. And here I'm actually introducing, making it a little bit more complicated, because I'm now no longer assuming that thing is 0. Okay, so I just wanted to write down, so you can write s hat as basically cos of theta plus theta 0, sine plus theta 0. So I'm actually allowing you to look at it actually keep the total coordinate of r fixed. Okay, so I have s hat that looks like that, and so here it is just drawn more carefully. So here you basically have r pointing there, theta 0 is this angle over there, and s hat, and this is your big R, and so s hat points along that direction, and so theta plus theta 0 is basically this whole angle over there. So basically this allows you to have s hat defined in the coordinate system that doesn't change. And so if I want to evaluate that integral number 2, which is, it's basically u evaluated at r, r hat, plus 0, the integral from 0 to 2 pi, times the delta function, plus t times this g2r, okay? And so this is effectively the derivative of g with respect to time, okay, that I just rewrote. And the reason I did it was to cast it in the same way as the one-dimensional thing. So this thing basically now has two terms. The first is the one due to the delta function. And what I have is basically the delta function at ct minus r, so I've just multiplied it by c. And if you look at this expression, it does not depend on the angle. It depends only on r. So you can actually split these two integrals. And it might seem like a trivial step, but if you can do this, it's very useful. You can split the two integrals. So what this thing is basically for a given r. So remember this r prime depends both on where you're evaluating the point and this big R. Okay. But you can basically, so what this thing now becomes is it becomes an averaged version of what u is around this little circle. Okay, because I'm integrating u's expression at the vector r prime, and I'm integrating it round d theta, okay, and r prime is now basically is parameterized in this way. So I have it at the origin at r, and then you have the r times s. So if I choose a certain distance for this r, this integral is simply the averaged value around that little circle of u. Okay, so, and then this delta function you can sort of work out. So effectively what you have here is this integral is dependent on r, just like when we were doing the mean value or the mean value theorem. That you have the same idea where you have a fixed point and you work out the average of the function in a circle around the fixed point. So this integral itself is dependent on big R, and the delta function allows you to evaluate it. Okay. And so the second term we're going to leave for a bit. Here it is. It's basically t times u of r. Also, where I've rearranged it, I've also got this average value of r around the circle times g2r dr. And so the first term, we basically have this, and what you have here, I've cancelled out the factors that are common, and you have that thing's equals to 0. Okay, and this is the reason why I made that derivative thing right at the start. And the reason it is 0 is that this average term is a function of big R, but the delta function forces you to evaluate the entire integral when this thing is 0, and you have a square root of that thing, so that actually cancels. Okay, so this thing is gone, yippee. And what you're left with is that U2 is actually much simpler than you could have, and you can work out, you can go even further because here you can integrate by parts. So you have this dg2 dr times dr times this integral over here. Okay, and that is your step function. And so what you are left with is you can take this DDR outside of both of them, and you basically now have this averaged value of u times your Green's function, how that's changing with r multiplied by t in front. Okay, minus t times how the step function is changing times g2r. Okay, so I've just used integration by parts. And the nice thing is that this thing is being evaluated at 0 and infinity. At infinity, we're going to assume that, well, the Green's function goes to 0, and we're also going to assume that the u usually goes to 0. And so you have that expression plus this guy, where you can actually rewrite this thing as just the gradient of u at r dotted in with s, and here's the Green's function coming in 1 over t squared c minus r squared. Okay, so if r is greater than ct, g2 is 0, so the top boundary of the first term vanishes. When r is equals to 0, g2 at r0 is just equals to 1 over 2 pi t, just from the definition of g2. And you have that, and you also have that this integral is simply 2 pi, the average value evaluated at the origin. So that's the field point at the origin. And so you're going to have that u2 is equals to this thing. Okay, and there's where it stops. So that u2 basically has the idea that it is the initial condition at the origin times ct, which is basically, so it's basically the initial condition over here times ct, which is basically this distance, times the gradient of the function divided by the square root. Okay, and that thing you have to evaluate it. What this effectively does is, remember with our just a one-dimensional thing, right? You had the initial condition here and the initial condition here that were picked out by the delta functions that contributed to the source point. What you have here is a different thing. You're making a Fourier series expansion of that function where the condition here is important, and in some sense the gradient as you go out is important. So it is slightly different from the two-dimensional thing. And what it incorporates is that this fall off happens as well. So it's actually permitting your wave, the impact of your wave at a particular point actually falls off with distance. And then just one comment over here, which should also give you a fright. When you see integrals, always immediately go to where they go to 0, because that's where all your trouble comes from. This thing is singular at r equals to ct, but it's not strongly enough singular, right? Because you can still work out the integral even though it's singular, right? There are these integrals that go over the square root that you can actually work out. And this is one of them. And to actually see that the integral is convergent despite this, you change variables, and you basically let r equals tc sine p. And what you then get is dr is just equals to that, and this divergent factor of dr over t squared c squared over r squared is simply equals to dp. So you can actually work it out. And what you finally have is this thing. And what you have is it's basically the gradient of the function So it's your idea of your Fourier series approximation of the function, except that if you are using the p variable, you're not working out the average gradient over the sphere, you're just sampling it at different points. Okay, so it's sort of an average gradient times by the ct, which is the radius. Okay, and okay, so this is basically the angularly averaged radial gradient, and is basically computed and at non-uniform distribution of points. Okay, so that's just what I said. And then the main thing is the contribution near the outer rim is the more heavily weighted. So this idea that over here for the one-dimensional factor, it was just these things were to contributing. What we have is that for the two-dimensional case, we're also going to have the boundary contributing more, but there is stuff from inside that is actually important as well. And so it comes out that way. Difficult to evaluate, but not impossible. Actually, once you get practice, you start getting a feel for it. But I just wanted to show you like all the steps of how to get there. Okay. The contribution near the rim weighs more seriously. And the other thing that you should note, suppose your initial condition has compact support. In other words, the function is like a hump and it goes away to 0. The important thing is that then if the function gets large enough, if you go far enough from the point, the central point, eventually that gradient is going to go negative, right? Because it's eventually going to fall off to 0. And so you have that state. So that becomes 0 for large enough r as the function decodes to 0. And this is unlike the one-dimensional case, right? With the one-dimensional case, you just had it, the wave propagating and going on. With this thing, or this term, basically, because this gradient becomes negative, eventually this term starts subtracting from what the function actually is as your time gets big enough. Okay, so you can actually see from that expression that the wave is sort of going to be a hump, and then it's going to propagate outward, but it's going to get smaller and smaller in amplitude. And that's what that thing actually is saying. Just another useful thing is at times t equals to 0, if you work out okay, so that's just writing what I'm saying. If you take the time derivative of this thing, okay, this is evaluated to t equals to 0, so it's not dependent in time. This term, if you take the time derivative over here, you basically have this term coming in. And that effectively is going to be what your initial condition, your time derivative actually is. But I'll show you that again more carefully. Okay, just to express the other two terms, which are actually the easier ones to evaluate, in the same coordinates, we have our Green's function that limits it to the cone. We have the source term, which is basically the Green's function that looks like that. And you can show, and you have this guy, your other term that comes from the time derivative of ut. You have the Green's function looking like this. Remember, I said r equals to c minus t minus c times t minus t prime sine p. And r prime equals to that thing, where the s is still the unit vector away from our new coordinate system. And r0 prime is equals to that. Okay. And that's simply the r0 prime is just what happens at the base of the cone. And so what you have is u1, you can then express this way. Okay, so the step function has resulted in that. You have your source term integrated over here. You are once again taking the average of the forcing term in a circle around your source term over here. And that this thing then becomes a function of big R. And then you take that big R and then you weight it with this factor. Okay, once again messy, but it's just written out so that when you actually do the example on your own, you have some guide of what integrals to actually go along. Here it is. Okay, I've just changed the variables in dr over here to dp, and that's what you get. And then I think you can simplify it further, yeah. And so I simplified it further over here, cancelled out the square root, which is potentially singular, just to show that it's not singular. And then you once again have the sine p weighting it out this way. And then the U3 component, you can write out to look something like this. And the one thing I wanted to say is U3 at the time derivative of U3 at t0 is simply ut at r of 0. Okay, I think I've lost. But you know that integral is actually equals to 1, and so something happened to my slides. Anyway, so you basically have that at times t equals to 0, right? You've got that the ut, this third term, ensures that you have exactly the initial condition at times t equals to 0. So that's actually also not so easy to see, is to see that when you write these Green's functions out, you actually have to be able to prove, and it's always possible, but it's not always so transparent to see, that at times t equals to 0, that you're actually getting back the initial condition as well as the fact that the derivative is equals to the derivative is equals to the derivative that you were given. And this is just proving that the derivative for this term is actually the derivative that you were given, and the reason is that this term's contribution just is at times t is 0, but its derivative contribution is exactly the derivative that you expected. Okay, so that's it. Sorry about the last line. Questions? Do you feel intimidated by the Green's function in 2 dimensions? Huh? A little. Have a look at it slowly. There's also a problem that once you work through it, you'll actually know. The main thing is you just have to keep your 2 coordinate systems, keep track of them. And also think back to your idea of your rubber sheet, that there's a very clear physical picture, and make sure the mathematics does that, and make sure the limits behave well. And then I actually put in a lot of details for the steps. I tried to put in all the details, so go through it carefully and actually see that you can follow what I've done. And if you can't, come ask me. In fact, come ask me tomorrow. That you can actually keep up with what I'm doing. These tricks are very useful when you do other calculations as well. So I guess that's basically why I put all the steps in. Because later on, if you try and evaluate similar things, it makes it easier. It's a big step up from working with one-dimensional to actually working with the vectors and the actual coordinates, the angular dependence. Even though the initial Green's function is beautifully simple, when you come to evaluating it, it's more complicated. But you've got to get complicated sometime. So, yeah. Okay, that's it for me, at least for the lecture part.